está ok.
Está
Está
excelente. Está
boa.
excelente. Está excelente.
Listo, profesor.
Pronto. Beleza. É, deixa eu fazer. Bom, eu vou fazer a introdução em português. Bom dia a todos, bom dia a todas. Hoje, a rede LATMAF, que é composta por várias universidades e centros de investigações da América Latina, tendo sempre oportunidade de todos os sábados apresentar um pesquisador da América Latina ou de outras partes do planeta. Hoje temos a grata satisfação de termos o João Belo, que vai falar da Universidade do Porto. Ou do Porto? A Universidade do Porto. Eu confundo com o pessoal de Aveiro, cara, por causa do Mário.
Pois,
É,
pois.
Universidade do Porto. Aliás, na Universidade do Porto eu tinha um amigo, um senhorzinho chamado Dr. José Ferreirinha. Não sei se você conheceu. Bom,
O nome, eu sou o nome. Eu não sei se alguma vez o conheci, mas já o ouvi.
legal. Então, então, o nosso palestrante hoje, João Belo, vai falar para a gente sobre o efeito magnetocalórico, que é uma grande, tem muita importância na construção de novos refrigeradores magnéticos que, bom, espero que vocês aproveitem bastante. Today we have the pleasure to announce the João Belo, a researcher from Porto University. He will talk for us about the magnetocaloric effect. Well, we have 15 minutes to talk for us, and go ahead.
Thank you. Thank you very much, Professor Isaías. Thank you very much to Mario Reis as well, that cannot be here. It's really my pleasure to be here. And I really, as I was saying, I really enjoy this idea of a joint university effort from South America, but also comprising other parts of the planet. So it's really a pleasure to be here. So exactly, my name is João Belo. I'm here to tell you about magnetic refrigeration from kinetics of phase transitions to the rotational magnetocaloric effect. I'll start. Oh, okay, sorry. So I'll start by introducing where I am from. So I'm from Porto. Sorry that this was a slide reused from a conference in the US. So Porto is just here in Portugal, north of Portugal. It's considered, so it's the second largest city after the capital, Lisbon. And the city is most well known by its port wine, which I guess most of you must have heard by now, but also by the beautiful landscape and riverside that we have of the Douro River. So in Porto, I'm based in the Faculty of Sciences of Porto University, which hosts our institute, which is the Institute of Physics for Advanced Materials, Nanotechnology and Photonics, IFIMUP. Okay, this is a photo, one of the photo, it has already some years now, about 5 years old. The number, it's updated, so we are about 120 members, comprising 40 PhDs, 25 PhD students, and 50 master students, who divide themselves in four main research areas, which are the quantum materials, advanced energy materials, where I belong mostly, and vibrational and ultrafast laser spectroscopies for biomedicine. So just to give you a very quick overview of our institute and what we deal with. So we deal obviously with magnetic refrigeration, but also triboelectrics, thermomagnetic generators, printable electronics, negative thermal expansion materials, magnetoelectrics, thermal switches, neuromorphic computation, energy storage in general. And we not only have a theoretical and simulation study, but we also have techniques to produce and characterize the materials, as you can see in some of these pictures. In fact, my topic, the topic of today, the magnetocaloric refrigeration, goes back almost 23 years, 23 years ago in our institute. This is our first institute paper on magnetocalorics. This is a very well-known magnetocaloric material. But okay, now jumping and focusing a bit on my main research areas, just to tell you a bit about it. So obviously the magnetocaloric effect, but also negative thermal expansion materials, and finally the multifunctional nanostructures for biomedical applications. Out of these three, the magnetocaloric is the one that I dedicate more time. But very interestingly, these three areas that seem very different have a common ground, which is magnetism and magnetic materials. So indeed, the main focus of today is magnetocaloric effect and magnetic refrigeration. And this is the outline of my talk. So I'll try to first motivate you on why do I believe that we are in the verge of a cooling revolution. So why do we need alternative cooling technologies? And then the talk will be divided into two main works, a more fundamental on the phase transition of magnetocaloric materials, and in particular their kinetics. And then a second part, more applied, more engineering, where I'll hopefully show you that by applying an alternative effect, which is the rotating magnetocaloric effect, we can have different opportunities, in particular for vaccine cold chain logistics. Then I'll close with a summary. Okay, I hope I don't take over time. Please let me know, Professor Isaias, if you can let me know 5 minutes or 10 minutes before the time ends.
No problem. I will
Thank you.
advise you.
Thank you, thank you. Okay, so why do I think we are in the verge of a revolution? So this industry, it's refrigeration, air conditioning, and heat pump, goes with the acronym RACHP. It accounts by more than 5 billion devices with 2.6 billion air conditioning units, 2 billion domestic refrigerators, which in total account for 25 to 30% of the global electricity consumption. This number always stresses me. So from the total global electricity consumption worldwide, 25 to 30 is dedicated to this industry. So economically, it's also a very important economy, accounts for 500 billion US dollars in sales annually. This is just expected to increase with developing economies in warm and populous countries like China and India and others. It's also a basic and ubiquitous need in food and medicine cold chain logistics, industrial and domestic space cooling. And in addition to the 30% of global electricity consumption, it's thought to contribute to about 7 to 8% of the total greenhouse gas emissions annually. Out of these 8%, one can divide 2/3 indirectly, because all these devices require electricity, which also implies the emission of greenhouse gases, but also directly 1/3, because of the leakage of refrigerant gases. So the cooling technology that we have relies on the expansion and compression of refrigerant gases, and a lot of these gases have a greenhouse gas effect, a direct greenhouse gas effect. Okay, so due to this problem with the refrigerant gases, from the 80s till nowadays, multinational agreements have been set and have been placed, in particular in Montreal, where in 2007, more than 100 countries agreed with the end of the hydrochlorofluorocarbons till this decade. Furthermore, in 2016, with the Kigali Amendment, another multinational agreement, the countries agreed on the reduction of 85% of the alternative gas, which was hydrofluorocarbon, up to 2050. These measures alone are expected to prevent the 105 megatons of CO2 equivalent emission, helping on this humanity mission that we have, that is to reduce the global warming. So in place, we are observing nowadays a major change to natural gas refrigerants, which include hydrocarbons, ammonia, and carbon dioxide, which do not have high global warming potential, but pose other threats as they are flammable, toxic, or require higher working pressures, which imposes a larger stress on this industry. Okay, so by now, this is my view of the industry. We are at a crossroad where we either continue relying solely on the vapor compression, or we try to invest further in alternative technologies. So as part of these alternative technologies, there is a large group called solid state technologies, in contrast with the gas expansion and compression. These solid state technologies include magnetocaloric, electrocaloric, and barocaloric. So the idea is that inducing an external stimuli, either magnetic field, electric field, or pressure, we are able to induce a temperature change in our material. So indeed, we can get this definition, we can reach this definition. A caloric effect is an entropy/temperature variation induced by an external parameter, be it the magnetic, the electric, or a pressure field. Okay, so now focusing on the magnetic refrigeration, the major advantages it has, it's the potential higher efficiency. So this is a very intricate discussion, and I don't want to go into too many details, but you have here a specific example where for a given COP, for a given device, one can get up to 20% higher energy efficiency. Simultaneously, it also has no refrigerant gas, so meaning that during the whole lifespan of the device, we will have no greenhouse gas emissions. There are two other minor advantages, which are also very relevant for the industry, which is the reduced noise and the reduced maintenance. Okay, so just grasping a bit the magnetic refrigeration thermodynamic cycle, you can see it schematically represented on your left, comparison with the vapor cycle refrigeration on your right. So this is a very well-known schematic. You can download it from Wikipedia, but I think it's very useful. So if we start with a magnetic material represented here in green at a given temperature, and we apply a magnetic field, we induce an extra temperature, a delta T, on the temperature, the initial temperature of our material. So our material warms up. So this is the first step. On the second step, we keep the magnetic field applied, but now we pass a heat exchanger, such as water or other gas, and we remove that extra heat while maintaining the field applied. That's why the magnetic spins continue to be aligned here. So now we have a magnetic field applied, but the temperature of the material close to the initial temperature. So now we remove the field, that's why this H equals 0, and we get a cooling of our material. The temperature of our material drops. And finally, on the last step, we pass again a heat exchanger, which basically is going to transfer the heat from the inside of our refrigerator to the material, to the magnetocaloric material, warming up the material to the same temperature as initially. So if we look, I'm not going to go into so many detail on the vapor cycle, but we can see that it's a very analogous thermodynamic cycle. Instead of having a field, we have a pressure, but then the rest is basically the same. Okay, we can also look at this in the entropy versus temperature curves of a given magnetocaloric material. You see here two curves, which represent the blue one, it's when we apply a field. The red one, it's when there's no field applied. So this magnetocaloric effect can be quantified very nicely using these graphs by looking at the horizontal and vertical curves. So horizontally, if we do this adiabatically, so meaning maintaining the total entropy of our system, this means that we will have delta T, and this we call the adiabatic temperature change. If we go vertically at the same temperature, so isothermally, we will have a delta S, meaning an entropy change of a given magnetocaloric material. So these are the two most important thermodynamic properties to quantify the magnetocaloric effect. So now trying to give a more atomistic but yet simple description. So in an adiabatic process, by definition, we have that the total entropy must remain constant, so the change in total entropy must be zero. If we now consider that in any condensed matter system, we can divide our entropy into three major reservoirs, the electronic, the magnetic, and the lattice, we see that we can add the changes in these entropies to get the total entropy change. Actually, for most of the magnetocaloric materials, the change in electronic entropy can be negligible. So we can just consider the magnetic and the lattice. So considering the first case, at zero field, we have our individual magnetic moments that are randomly oriented. So there's no field to induce the anisotropy and the order of our spins. So this is in fact a high magnetic entropy state. Whereas when we apply our magnetic field, the spins align along the magnetic field, they become parallel to it. So individual magnetic moments align with the field direction, reaching a low magnetic entropy state. So this means that when the field is applied adiabatically, our entropy, our magnetic entropy is reduced because we go from a high to low magnetic entropy state, meaning that okay, so now if we consider that we are in an adiabatic process, the total entropy must remain constant. This means that the lattice entropy must increase. This is the same to say that temperature increases in our given material. Okay, how can we measure this effect, in particular the delta T? These are very rough examples of our setup at Porto. So I'm an experimentalist, so I typically enjoy these experimental details. So here you can see gadolinium plates are here. We can set, so the biggest key points that we need is the magnetocaloric material, a cryostat, and the magnetic field. So for the gadolinium plates, we see here one plate with a thermocouple. Ideally, you have to have two magnetocaloric plates and the thermocouple is sandwiched in between the two. We can install it in a copper cold finger, place it in the cryostat where we can control the overall temperature of the material, and then we can apply magnetic fields using either an electromagnet or an Albach array of permanent magnets. Just to give you a very quick example, you have here the same cryostat that I showed you in the previous slide, but now closed. And here on your right, you see a lab view plot of the temperature versus time. And you will see very clearly this jump in temperature when a magnetic field, the permanent magnet, is applied. You will see it in a few seconds. Here it goes. And you see the very rapid jump in temperature and then the natural cooling down of the material. The same, the opposite happens when we remove the field, as you will see now. Okay. Yeah, exactly. And then warming up to restore the temperature of its ambient. Okay, so we have entropy and temperature. And here I present you two of the benchmark magnetocaloric materials. It's gadolinium and gadolinium 5 silicon 2 germanium 2 alloy. Here on your left, one see the change in magnetic entropy for gadolinium. Those are the open symbols for a 2 Tesla field at different temperatures and for a 5 Tesla change for different temperatures. In solid lines, one can see the alloy, the 522, in solid lines, again, for the 2 Tesla and for the 5 Tesla. Okay, there are much more materials. So gadolinium discovered in the 80s, and then the 522 discovered in 97 really were really major triggers to draw attention of researchers and industry to this technology at room temperature. And so since then, a wide range of different magnetic materials have been discovered, which have a magnetocaloric effect very high at room temperature. Another case studies are iron rhodium, the lanthanum iron silicon, the Oisler's nickel manganese indium, and much more. Very interestingly, there are also magnetocaloric materials which have their effect maximized at cryogenic temperatures. So you see here the delta T for different temperatures in Kelvin, and you can see here effects of 6 and 7 Kelvin and even more at below 40 Kelvin. Okay, so in terms of industry, where are we? Is this technology already being used? Yes, it is. It's not, let's say, worldwide spread yet, but there is a very well-launched German company called Magnotherm, which has launched this Polaris refrigerator. Now, more recently, they have also launched another product, and you can officially buy a magnetic refrigerator to this company. Also, there are other very interesting projects in academia and on a merge between academia and industry, including this helical. Helical, it's expected to be a hydrogen liquefactor using magnetic refrigeration principles. So hydrogen liquefacts at 20 K. And in fact, just 2 weeks ago, this project showed and advertised its first assembly of this hydrogen liquefactor, magnetic liquefactor. Very interestingly, and perhaps the oldest application of these effects is indeed on the cryogenic range. So Q-Ultra, another German company, is using this effect to cool down to the millikelvin region using the magnetocaloric effect for quantum computing applications. So as I hope I was able to show you, from Magnotherm to Q-Ultra, this effect can be used for room temperature cold chain applications, hydrogen liquefaction, and millikelvin for quantum computing. So it's a really transversal technology and very important because of that. Nevertheless, as you might imagine, there are still major challenges to be overcome. They are very nicely and schematically represented here, where we see the most important thermodynamic parameters from the materials point of view, but also from the device's point of view on your right. So my first scientific work to present today is focused on addressing the time dependence and frequency of these materials, which in my opinion is still very poorly studied in the literature. And so that's the motivation for this first part. In fact, a motivation goes all the way back for the motivation of studying phase transitions, because if we look at the expressions of the delta T and delta S, we see a common factor in them, which is the derivative of the magnetization in order to temperature that is present in both parameters. So this means that both the delta T and the delta S are maximized at a magnetic phase transition temperature. So in a para to a ferromagnetic state in the Curie temperature. So this just an example of a magnetization versus temperature curve, and our effect is maximized exactly at the TC. In a bit more general terms, the phase transitions can be generally classified into first and second order, depending on if their first derivative of free energy is discontinuous, like here, in contrast with the second order, where you can see here that no discontinuity is present. And in the first order, typically happens the release or absorption of latent heat, and we can also observe an hysteretic behavior, meaning non-reversible irreversibilities in our cycle. So I really like this quote by Bin and Rodbell from the literature, where he states that for first-order phase transitions, the situation is like that of a man who has run beyond the brink of a cliff, so there is no gentle way down. So we really have very abrupt changes on our order parameters. So a second order, in contrast, is one where the first derivative of free energy is continuous, and only the second derivative presents discontinuity. In this case, the entropy versus temperature, as we can see here. Okay, so these just schematically show, this means that we are able, in a given phase transition, we are able to change from a low order, high entropy state, a paramagnetic state, to a ferromagnetic state, which has high order and low entropy, meaning harvesting a delta S in between the two states. Okay, typically in these materials, for example, the lanthanum iron silicon is a classical example. These phase transitions, these first order phase transitions, are accompanied by a major structural change that you can see represented here by the lattice parameters of this cubic lattice, or the volume change. So this material presents a negative thermal expansion as it contracts of about 1 to 1.5% on warming up or when applying field. Okay, so a first order phase transition in these materials is typically when there is a coupled or nearly coupled transition between the magnetization and the lattice, the structure of our material. So coming back to the graphs that I showed you before, we see that for the gadolinium silicon germanium alloy, you see the effect is larger than for gadolinium, exactly because for gadolinium silicon germanium alloy, we have a first order phase transition, in contrast with the second order phase transition presented by gadolinium alone. Okay, the same, this importance goes, and I told you that we can have magnetocalorics with a magnetocaloric effect at different ranges in temperature. So it's really a thing of tuning the TC, the transition temperature of your material, and then you tune the application of your magnetocaloric material. Okay, so the motivation for studying this phase transition kinetics goes on from an application point of view, the idea to enhance this device's efficiency. So if we look at a given device, we can estimate its maximal specific cooling energy simply by multiplying the TC by the delta S at TC. So this is what we call a specific cooling energy, the maximum specific cooling energy of a single material. And it's here represented. So now if we look at theoretical maximal specific cooling power of a device, not a material anymore, already a device, here you can see a prototype example from General Electrics. We can see that we just need to multiply these two guys again times the frequency of operation of our device. So this is just to say that the device performance, the amount of heat that is being transferred, is directly proportional to the frequency of operation. This is also seen in this graph here for different applied fields. However, this is not so simple because there is a full thermodynamic cycle that should go on. So there are limiting factors, which are the fluid, the heat exchangers, friction losses, and heat exchange times. So the heat being transferred from the material to the heat exchanger takes time to occur, but also, and that's the point that most interests my research, the time the materials takes to respond to the stimulus, to the application and removal of magnetic field. Okay, so just taking an example, looking at the full cycle represented here, we see that, for example, if we take a frequency of operation very low, 1 Hertz, one would need 1 second to go through all 4 stages. So there are 4 stages, meaning that in a rough estimation, we can have 250 milliseconds for an adiabatic heating or cooling process. However, literature shows us that materials presenting this high magnetocaloric effect are typically on the time scale of tens of seconds to tens of minutes to undergo the full transition. So this is really an important issue. I show you here some examples of the gadolinium germanium case where in specific conditions the transition can take up to 50 minutes. Iron rhodium, it can take up to a few minutes. Lanthanum iron silicon, again, a few minutes to some seconds. So this phase transition can be quite long. And okay, my goal was to try to better understand what's happening on this phase transition kinetics. So what is taking these materials so long to respond to the stimulus? So at the beginning of this study, we picked 3 main archetype materials: the lanthanum iron silicon, the iron rhodium, and the gadolinium 5 silicon 2 germanium 2. The results I'm going to present you today are focused on the lanthanum iron silicon. Okay, just to revisit this material has a cubic atomic structure with this space group. It undergoes, as I told you, an isostructural phase transition, meaning it retains the space group, but it contracts at the Curie temperature. It contracts a lot, about 1 to 1.5%. In its present form, the transition is at 200 K. However, we can either via hydrogenation or other chemical substitution, we can shift this temperature up to room temperature. So it is isostructurally, this means it's an isotropic change in the lattice, and it has a negative thermal expansion. In the magnetic part, we see that it has a paramagnetic, so high temperatures, paramagnetic to ferromagnetic low temperatures state at 200 K, an abrupt and with thermal hysteresis magnetization versus temperature curves, as you can see here. This transition can be induced by magnetic field isothermally, and the TC, so the temperature at which the transition occurs, it's highly dependent on the magnetic field with this given range. So depending if we have a 1 Tesla applied, that's going to be 4.6 Kelvin above the Curie temperature. Okay, so this material has a strong magneto-volume coupling and presents a first-order phase transition. Okay, so let me place it all here. Our biggest motivation at the time was the paper by Edmund Lovell from Imperial College in Advanced Energy Materials in 2014, where he did a very interesting experimental protocol, which was what became termed as the H-pause protocol, where basically we sit at a given temperature very close to the Curie temperature, but slightly above, so in this case 3 Kelvin above. We sit there, very stable. We apply a magnetic field up to a given H-pause value, and different H-pause values, this parameter can be changed, and then we just measure the magnetization as a function of time. So here are their results at that time, magnetization versus time for different H-pauses, where you can see for all of these different curves, they were offsetted so that at t equals 0, for all the curves, the field reached the respective H-pause value. So this means that all that you see after t equals 0, time equals 0, is magnetization evolving just as a function of time. So there are very interesting features here. The magnetization can be nearly unchangeable for the first 10 seconds. The total available magnetization change is only reached after 40 seconds, and some other very interesting points. So this leads me to the other motivation of this work, which is scientific. So in these first order phase transition materials, it's a bit of a chicken and egg question of who is driving who. is the magnetization driving the structural transition or vice versa? Also, it's very important from a scientific and technological point of view, to understand how these kinetics vary with temperature, field intensity, the field sweep rate, so how fast we are changing the field, and also how it depends on the intrinsic, but also extrinsic properties, such as the thermal environment of the sample, how large or small the sample is, and so on. So let's try to find out. As I told you, this was our archetype, lanthanum iron 11.6, silicon 1.4. It presents these very beautiful magnetization versus field curves. And the goal is to perform a comparative study of the structural versus the magnetic, the focus of Edmond Lovell work, transition dynamic study. So in order to do this, to study the dynamics of the lattice, we went to Brookhaven National Laboratory in the US, in particular to NSLS-2 synchrotron with this beamline, where the beamline scientist is Melinda Abekun, a very brilliant beamline scientist. So we chose this synchrotron because of the high brilliance that enables fast and statistically good XRD pattern acquisition, and the ability to apply magnetic fields up to 5 Tesla with different sweep rates, so different velocities. So this, just to show you an example of an XRD pattern of this material, and this was achieved with a 1.5 second acquisition. So with these patterns, we can do Rietveld refinements, and then we can take out the lattice parameter, the interatomic distances, and so on. So our first goal was to perform equilibrium temperature-dependent refinements. We have here the lattice parameter as a function of temperature for heating and cooling curves to find the exact TC of the material. Then we picked this TC, added 4 Kelvin, and seated there very nicely, and applied the H-pause protocol. So here is a representation of field versus time, and here on your right is a representation of intensity of the XRD pattern versus 2 theta of the XRD pattern, focusing on the most intense peak of this pattern. So this pattern in blue was taken at this point, 0 field, before field started changing. This other blue one was when the field reached the maximum value. We can see a shift in the peaks as expected. But then all these other are just time dependent. So we can really see a time dependence evolution on the peaks of XRD, which is intrinsically associated with a time dependent lattice structural transition. Okay, so to our knowledge at the time, this was the structural transition kinetics measured for the first time on magnetocaloric materials. And so we took this opportunity. We were very, how can I say, skeptical at the time. So our first job was, okay, let's do exactly the same, but no field applied, and see if this change in the lattice parameter is just because there are thermal fluctuations. But you see here that with no applied field, nearly the lattice parameter remains constant, in contrast with the applied field red curve. And so by really knowing the lattice parameters, we could estimate the high volume phase fraction, which we call FM from ferromagnetic, and the low volume phase fraction. And then we can plot this average lattice parameter. Okay, so by doing this for different H-pause fields, these were the curves observed. So you can see very long relaxations up to 200 seconds. This green curve, even after 500 seconds after the field has been paused, is still evolving. And so by looking at the literature and studying, we decided to apply this KJMA model based on the Avrami modeling of chemical reactions and phase transitions in general. And we applied this model to fit this data, where these parameters, K, is related to the activation energy required for the phase transition, Eta is called the Avrami exponent, associated with further physical meaning that I'll give just after. And these are just the saturated values and the relaxations contributing to the final value. Okay, so the K value and the eta allow us to take the typical relaxation time, so how long the transition takes to occur. And yeah, just to summarize what we observed, so we see a very significant change on the saturation value in the sense that they do not always saturate at the same value. There's an evolution. The higher the field, then it gets, we see that almost all curves saturate at the same value after a given magnetic field value. That the time scales also strongly evolve. We can see that, yeah, this was the extreme scenario, but in contrast, this 2.1 Tesla curve rapidly relaxes and stabilizes in its saturation value. This is already different from what Edmond Lovell found out for the magnetic counterpart, where we saw that the saturation value was always the same for the different H-pause intensities. In the other hand, the timescales do seem to evolve in a similar way. Perhaps more interestingly, what we observed was an asymmetry between when the transition is forwards or backwards. So forwards meaning when the transition is driven by field application, and backwards when the transition is coming back, so upon field removal. So you see here again the lattice parameter for 4 different H-pause values. We see the very long relaxations. And now we applied a similar protocol, which was basically just remove the field to 0 value and continue to track down the lattice parameters. So we see that all these curves were shifted so that at t equals 0, all of them have already reached the field 0 condition. So there is no relaxation after the field has reached the 0 value. It's a very striking asymmetry between application and removal. And this led us to ask to our colleagues at the University of Aveiro to develop a magnetovolume model, which can be summarized by this Hamiltonian to simulate what was going on. So this was what they did. Here you see the Gibbs energy in the counterplot. So the more red the color, the higher the Gibbs energy. Sorry, the lower the Gibbs energy. The lower in terms of in negative, I mean. The same here. So the difference between the two is that this is a 0 field condition. This is a 2 Tesla field condition. So the major difference we see is that for the 0 field, there is 1 absolute minimum, whereas for the 2 Tesla case, we have 2 relative minima. Okay, if we plot it in a 2D graph, so just the logarithmic of the Gibbs energy as a function of the lattice parameter for the 0 and the 2 Tesla case, this is what we see. And now, if we look again at the relaxation upon field application, we see that for the application, so for reaching the 2 Tesla, for example, for the states to evolve, it does have to overcome an energy barrier to go from 1 local minima to the absolute minima. So this is the energy barrier height that the state has to undergo, and that in our interpretation is strongly connected to the kinetics of the phase transition, meaning that the larger the barrier, the more time it should take for the system to relax. So indeed, if we plot the time scales of the relaxations as a function of the energy barrier heights, we do see a linear behavior. And this was very interesting to note because these were just modeled, whereas these are experimental results. We see a very nice linear behavior. In contrast, when we remove the field, we go to the black curve. And here we see that there is no barrier height, so that the transition occurs much faster. So this work has been published and is available here at Materials Today Physics from last year. Obviously, any other question or comment that you might have, please let me know. I'm sorry that I know that I'm approaching the end of my time, but just to quickly jump on to the second part, just on this, sorry, still on the kinetics, we
João,
do have
you have 10 minutes.
10 minutes. Perfect, perfect. Then it will be very perfect. So just to finalize this first part, I would like just to let you know that more recently at the High Magnetic Fields Lab in the Netherlands, in Holland, these two very bright master students have developed a new setup that enables us to simultaneously measure strain, magnetization, and temperature, which then allow us to very nicely, because we are measuring at the same time, decouple these magnetic and structural phase transitions. So just to let you know, in case any of you, or in case you know of other colleague might have a sample or a material where this setup might be interesting to be used, please just let me know and I can tell you all about it. Yeah, so just to leave you this. Okay, so now for the second part, a new twist, a rotating magnetocaloric effect based on demagnetizing effect. Okay, so I showed you already this graph. Now I'm going to focus on the right part of this graph in particular. So the right part is dedicated to the device's challenges. And one of the device's challenge is the field utilization, meaning that in most built prototypes, magnetic refrigerators, the field source accounts for over 50% of the total cost of the prototype. Moreover, they are also very heavy and costly. So, okay, first point. So this is really a major issue in economic terms, right? If we need to decrease the price of fabrication of these devices, then we really need to look at the field, the field generation. And also on real prototypes, the efficiency needs to be improved to achieve larger temperature spans. So this 50%, you can check it at this reference by Rasmus Bjork. But well, just to resume, so magnetic refrigeration major pros are higher energy efficiency, environmentally friendly because it doesn't have any global warming potential materials. It is non-hazardous nor flammable or toxic, in contrast with the vapor compression. But this has also some cons. So it relies a lot on critical raw materials, both on the magnets, so the piece that generates the magnetic field, but also on the magnetocaloric material. This is under a lot of geopolitical vulnerability, as you all know. So it requires a permanent magnet, that it's bulky, it's complex to design and costly, and also it needs to have high performance. Okay, but what if instead of applying and removing a field, we just kept the field intensity constant, but just rotate the field vector? So going from the conventional magnetocaloric effect to the rotating magnetocaloric effect, the potential pros on going to rotating versus conventional are the even higher energy efficiency, because very likely we'll need less input magnetic energy to change the material position, and we could get a smaller and simpler device. Okay, the rotating magnetocaloric effect has in fact already been studied in the past 20 years. We can now think of it and understand it as the material entropy as a function of magnetic field angle, theta, so not only intensity anymore. And this effect has been studied very thoroughly in single crystals, which have a strong magnetocrystalline anisotropy. So these are a few examples: dysprosium phosphate, neodymium cobalt 5 single crystals. We can have delta T's of above 1.5 Kelvin at relatively low fields. So very interesting. Very interestingly, there are cases where we can have a rotating effect larger than the conventional effect. And these rely on the easy and hard access magnetization axis, and also on spin reorientation transitions. Those are the physical phenomena behind it. So the cons of this are, in fact, the use of single crystals. So it's impossible to think that we are going to need a 1 kilogram magnetocaloric material, which is a single crystal, because single crystals are very costly. They typically have small masses, very hard to produce, and so on. Okay, but what if we could observe a rotating effect in polycrystals? Okay, sounds a bit funny. Indeed, we can think of having a rotating effect based on another anisotropy, which is a shape anisotropy. So the shape on magnetic materials is very important for the demagnetizing effect. This effect indeed reduces the effective internal field in a magnetized sample in this way that can be seen here on this expression. So the internal field within the volume of our magnetocaloric material is the external field plus the demagnetizing field. The demagnetizing field, it's the product of N times M the magnetization, and the demagnetizing factor. So a large demagnetizing factor means that the internal field will be significantly reduced, and delta T also reduced. Okay, so we can use this anisotropy, this shape anisotropy, in particular in a plate. A plate is a very good example and easy to follow. So in a plate, if we apply our external field, so this is the plate, something like this. If we apply the field perpendicular, that's where the demagnetizing field will be largest. So meaning that the internal field within the magnetocaloric sample volume will be smaller than the external field. Whereas when we apply the field parallel to the plate, the demagnetizing field will be very small, meaning that the internal field will be roughly the same as the external field. So rotating from one position to the other implies a change in the internal field, which is delta H int. Okay, this just to quickly give you some demagnetizing factors of different shapes. So a plate as near 0 on the plane. If it's perpendicular, it's almost 1. An ellipsoid as different along the different axes. A sphere has the same value in all directions because it's it's isotropic. A cube similar to, and so on. So this N demagnetizing factor is shape and orientation dependent. So by rotating, again, taking the example of the plate, the field applied perpendicular to the plate, and we are lying here in this S versus temperature curve. If now we rotate the field or rotate the plate, either ways, we just have to change their relative position, relative orientation. We indeed change the internal field, so we get a different S versus T curve, and therefore a delta S and a delta T. Okay, in fact, we found out later, this was already partially discovered by John Barclay in its patent from '84 in a gadolinium plate. However, here in Porto, we decided to investigate this further, and by using the setup that I just described you, but also simulated data, we are able to measure the delta T under a 1 Tesla field intensity conventionally along when the field is parallel to the plate. The orange one is when the field is perpendicular to the plate. And finally, this reddish one, smaller one, it's upon rotation. So the field intensity is the same. We just rotate the plate and we get a delta T. This is a schematic video of our infrared camera. We have a Hallback here, and we have a magnetocaloric plate here. And you see the change in the temperature, the overall temperature, by just rotating the plate within the magnetic field. Okay, So we found these, we decided to properly characterize this effect for different field intensities, and this was what we observed. Very interesting behavior, highly non-linear and seems non-monotonous. And in fact, if we look just at the peak values of the delta T as a function of the field, the external field intensity upon rotation, we see that this effect saturates. So it's really irrelevant to have very large field because you are not going to have a larger delta T with a larger field. So this effect saturates actually at 0.5 Tesla for a gadolinium plate. So this tells us that in a magnetic refrigerator relying on a rotating magnetocaloric effect, one does not need a large, heavy, or costly magnetic field intensity permanent magnet. Okay, this was our comparison of our polycrystalline delta T figure of merit in comparison with the literature. We were very nicely placed. Now we are also studying other conventional magnetocaloric effects upon rotation, like the gadolinium 5 silicon germanium, but also lanthanum iron silicon and some others. This initial part of this study was published on Journal of Physics Energy, highlighted as one of the best papers from 2024, and also it's under patent pending, these major results. Also, and very importantly, these results were the first initial step that we needed to apply to EIC, to an EIC Pathfinder project. EIC stands for European Innovation Council Pathfinder. This is one of the branches of the European Union focused on the funding of fundamental and applied research. And so we applied for this project that we called MAXIN, Clean and Efficient Cooling in Vaccine Transportation using Rotating Magnetocaloric Effect, together with other 6 institutions from Europe and a very broad advisory board. And why we aim to use this technology for vaccine cold supply chain? Well, it's very sad actually to get acquainted with this information, because we know that every year more than 1.5 million people die from a disease that could have been prevented with vaccination. And paradoxically, more than 50% of the produced vaccines are reported to be wasted. One of the major reasons for this wastage is the improper temperature control along the cold chain of vaccines. Okay, with this, I would like to thank to all my colleagues, but also to the funding agencies that supported this work. And I would like to thank you and leave you this message that in case you know of any PhD students or postdocs that might be interested of joining our group, please just let them know, and we are always looking for motivated students and postdocs. And that's it. Thank you for your attention, and I'm open to any questions or comments that you might have.
Thank you very much, João. Excellent talk. Excellent. I like so much this study of the magnetocaloric effect. I studied it for a long time ago. Now I'm working not with magnetic materials, but with watts in superconductors.
Wow.
Okay, and when you told about the magnetization factor, it was for me very interesting. Of course, a lot of other parts, it was very interesting. However, I have 2 students and more persons. We submitted one paper to one review, one journal, and talk about the geometry of the cylinder. And it is it is connected with the demagnetization factor, and it has it show for us different answers in the magnetocaloric effect in terms of the withdrawn heat of the environment. And it was the magnetocaloric effect was calculated in function of the temperature, and we could observe. You see, it's a theoretical work, and I could realize that there is a determined temperature where there is an inversion of temperature. What is, well, the talk yours is not mine. Okay. I
No,
don't have
very
a question,
interesting.
but I have I like it so much, your talk. I remember several things when I work with magnetic materials using magnetocaloric effect. Well, one more time, thank you very much for your talk, and I will open question sections. Uh, uh, I will call to do the first question, Professor Stewart. Professor Stewart.
Professor Bello, thank you. Thank you for your very clear presentation. I have one or two small questions. It's partly because of my lack of understanding. You showed the 522 alloy, the change in entropy with temperature, and it had some structure to it. It wasn't just a single peak with a relaxation.
Let me jump
Yeah, it's a bit
back.
early on, yeah.
Yeah, sorry, these were too many
That's
slides.
okay.
You mean on the delta T versus
It
temperature?
might have been, it's either delta S versus T or delta T.
I think I know what you mean. Very,
You
very.
compared different, this one, yeah. The one on the left,
You mean
so there's
this?
a shoulder. Is that just
Very good.
the different contributions appearing as you change the temperature?
Very good point, Stuart. Very, very well seen. This is, in fact, so at the time, this is from Pesharsky's and Geschneider's paper, or the first paper on this composition. At the time, they didn't know this because they were just starting to look at it.
Yes.
What this is so this alloy, it's a bit difficult to produce. So you typically hard melt the three materials, the three reagents.
Yeah.
Then you need heat treatments. And what very often happens is that you end up with two phases. So they are, okay, let me try to there are two structural phases, not metallurgical phases. So the metallurgical phase is 5 rare earths for 4 transition or silicon germanites. But within that 5-4, you have two structures that are possible. One called orthorhombic and the monoclinic. What you want for magnetocaloric enhancement is the monoclinic. That is the one going the first order phase transition. But you end up, even after a lot of thermal treatments, with always 20 to 10. I mean, the best case scenario I saw was about 10, I think, of this orthorhombic, which is a different structure and has a different TC, higher TC. So it has a TC at about 300. So indeed, what you really nicely saw, this can be deconvoluted into two peaks, where the high temperature peak is the magnetocaloric of that phase. So it represents. Was I clear? I'm sorry. Maybe I was. What I'm trying to say in a MH is this. Let me try if I can write here. Sorry, Professor, because in MT this is very clear. I'm not sure if I'm gonna be able to draw here, but let's try. Okay, what I'm trying to say is that if we look at the magnetization versus temperature curve, okay, you apply a small field and then you measure magnetization of this compound. Then what you would observe is something like this.
Sure.
Something like this. So the orthorhombic has a TC here that leads to this delta S at higher temperatures. And the monoclinic one is the larger one at slightly lower temperatures. That's why this structure on the peak.
Thank you. That's very, very nice explanation. Thank you. You also showed some different materials. Some of them were manganese. Some of you showed the Heusler alloys, nickel, manganese, antimonide. You showed manganese arsenide. There's a table comparing them. This one here. I spotted manganese arsenide. I mean, manganese arsenide is a semiconductor. I've worked with manganese arsenide. Is it really useful for this type of physics that you've described to us?
Yeah, it's a very curious example. Also because of the arsenide, also, right?
Yes,
It's
yes.
very toxic, and so this was ruled out immediately to be used in a refrigerator.
Okay.
But it came out as a good, let's say, playground for scientists to play
Yes,
with.
yeah.
So it eventually led to this family here. It's them. I'm almost sure. These manganese, iron, phosphorus, germanium, or silicon.
Yeah.
They derived from this. So people eventually started performing chemical substitutions and got to these with germanium or silicon, and then there are other formulations also. But yeah, so to be direct, it was and it's still studied from a purely scientific point of view to better understand the transitions and so on. But now people look at this neighbor alloy to be used in a real refrigerator.
Yes.
I don't know.
Thank you.
I don't
It's
know
very
so much.
interesting. Thank you for that comment. I mean, some of these materials are useful for spintronic applications. They're so-called half metals. They're very interesting to make spintronic devices. It's very interesting that there are other applications for them. So that's great.
No, yeah. The iron rhodium, it's another example that it has been covered also for spintronics applications.
Yes.
So it's a very transversal material also. But again, because of rhodium being so expensive, it's just comes up as interesting from a scientific point of view, not from an application. Yeah, I'm sorry, I don't know so much more about the arsenide, but
on the subject. That's fine. Thank you for answering my questions, Professor Bello. Thank you.
thank you.
Thank you.
Thanks, George. The next questions come from our friend Julio Guzman.
Sorry, can you hear me?
Yeah.
Yes, I'm in a quite noisy place. Sorry about that. Well, thank you very much for the presentation. It was really nice. I think you touched very important concepts in solid state science. You know, I also have two small questions, but maybe I can frame them into one. If you go to your slide 61, I think you were showing time to solve dynamics there.
Yeah. Here?
No, maybe it was before. It was before, maybe 56, something like that. Yeah, that one, for example. Oh yes, that one is even better, the 54. You know, when you were giving your talk, I was really thinking about nucleation growth versus spinodal decomposition. So I was wondering if by further decreasing, getting away from the critical point, you were ideally, you should increase the conjugated the field in this case to arrive to the spinodal line. So I was wondering if you saw further increase of the dynamics, if you have done any in-depth study about how dynamics look like when you follow the spinodal line. Rather, yes.
That's really a good question, Julio. We haven't done yet. That's something that we are pursuing at the moment. This came to be honest, when I got into reading this first motivating paper, this Edmond Lovell here in the bottom. I even had barely heard about the kinetics of phase transitions at all. to be completely honest. And so even the appliance of this Avrami model has been, so this all just to say that I'm kind of new to this topic, and I'm still trying to learn, and this is something that we are lacking, I feel, of a more theoretical and thorough comprehension of what is going on exactly, and how can we decouple all these types, and how can we why nucleation, I mean, when nucleation is happening first, it's obvious, but really quantifying the nucleation, the propagation mechanisms, this is all, how can I say, now we are looking at this field, and it's so much things that we wanted to do, and so much harm, so few arms. So no, unfortunately not. We haven't looked at it, but it's something that we want to do. We are hopeful that now with that setup that I showed, specifically on this, because that was one of our starting questions, was, okay, we have a magnetic and a structural phase transition. They are supposed to be coupled, but what does this coupled means in time meaning? So really means that they are happening exactly at the same time. So every second we get 10% more of magnetic phase transition and structural phase transition, or one is lagging the other, or you need to get a threshold of one to initiate the other, all this kind of stuff. We are now getting data of with this setup, because and this we can say with this setup alone, because we are measuring all three: magnetization, structure, and temperature simultaneously. Yeah, so sorry. No, the simplest answer was to say no, we haven't looked at it, but we are very much eager to do it. Yeah.
No. Thank you very much.
No, thank you. Thank you.
Julia, Julia Guzman.
Yeah, sorry,
Okay.
yes.
Could you understand our Portuguese language? I read your
I
because I
made a
read
number at the beginning.
your comments. Okay,
Yeah,
no
I
problem.
will.
Okay.
Well, we share a lot between Spanish and Portuguese, so
Yeah.
more or
Okay.
less, more.
The next is Professor Tauisi. I can't speak your name correctly, but it's Tauisi.
Actually,
Okay.
it's Clauise.
Tauisi. Oh, thank you very much.
Good morning. Thanks for your talk. Regarding this structure, the cubic structure that you dedicate a lot of time, this lanthanum, is important because it's just an expansion and contraction, or what is the reason that is interesting for you, this, specifically this structure? What is the reason you dedicate a lot of time with this structure?
My main interest was because this is a well-known magnetocaloric effect, lanthanum iron silicon, stabilizing in this cubic structure, where we see the lanthanums here are the golden guys, the iron is the red one, the iron 1, the iron 2 are the blue ones here. So my main interest came from the magnetocalorics. And then for this study, we wanted to understand exactly this decoupling between, the structural part and the magnetic part. So the magnetic part, this kinetic study had been done by that Edmund Lovell. So that part was very nicely characterized in terms of magnetic phase transition kinetics. And then, because we knew that that phase transition has a isostructural transition occurring, so it's a magnetoelastic, formally speaking, transition, we wanted to study from the structural part. But it's a very good question. I mean, so this is where we came from. But then, as we saw, this material also presents a very interesting behavior, which is the negative thermal expansion behavior. So even with no field, so regardless the magnetism that it is there, that is obviously playing a role, but if we just look at the volume of the material, we see, and I think I showed that in a previous slide somewhere. I'm sorry about this. Yeah, here perhaps you can see, and this is this is data from our group. We see that the volume, so this is the relative change of the volume, is negative. So the volume of the unit cell contracts, and it contracts isotropically, meaning all the lattice parameters, because it's a cubic lattice parameter. So this is also very interesting. I found it very interesting for negative thermal expansion applications. So one can think one of the most basic and already used nowadays is one can think of mixing a negative thermal expansion material within a composite, which has a positive thermal expansion. And by adding these negative thermal expansion particles, for example, one can reduce the overall composite thermal expansion coefficient. And this is very relevant for space applications, for telescopes, where large temperature changes can lead to mechanical cracking and mechanical deviations and so. So this is a bit of the side projects that I have. But yeah, I'm not sure if your question was this, or if you wanted more detail on the.
No, thanks for your response. I mean that because this is a centrosymmetric structure, I'm expecting that the more important role is from the iron in the center. That's the spin, right? Is the more important element in this structure, because the others, they are acting in the opposite direction.
Opposite directions, no?
So the more important thing is the red one, is the iron. So maybe, and this is interesting because this is a cubic and an icosahedron. I saw in this structure, icosahedron, the cubic. I like this structure. Thanks for your talk.
No, definitely, Professor. For sure, there is and for sure we even have in our data, because now we have a lot of synchrotron data on this material. So I was also wanting to understand atomically what is happening, right? Unfortunately, I still didn't have time to go through it, but it's a bit. How can I say? It's a bit frustrating because very likely I have the data. I just need time to analyze it to make these kind of claims, let's say, to better understand atomistically what is happening, right? Thank you.
Thank you, Telahus, for the question. Thank you, John, for your answer. Professora Gabriela from Córdoba doesn't have a question, but she thanks you your very good presentation and subject.
Thank you.
The same is thanks your presentation, Professor Arturo from Mexico. And now Ximena Velázquez from Universidade de Colombia.
Buenos días. Good morning, everyone. Good morning, Professor Isaías. No, in this moment, we don't have any questions from our network from YouTube. In this moment, the people only say thank you for this interesting talk. Thank you so much.
Thank you for listening.
Thank you, Ximena. Professor Sérgio Paniagua.
Yes, hi, thank you so much for that wonderful talk, Professor João. It was very educational, and I'm all excited about buying a magnetocaloric refrigerator soon. In fact, I wanted to ask you, how much research are the big players in refrigeration, like Samsung and these kind of folks? How much are they doing, and how much are they sharing in papers?
Yeah, very good point, Sergio. So, and this to be first of all a disclaimer. I haven't been really updated with all the industry and all the movements that have been going on. From what I know, let me go back. So Magnotherm, it's really in Europe, at least, it's really one of the major players because they emerged. So they are a brand new company. They have 5 years, perhaps. I'm not sure, 5, 7 years, something like this. And they emerged from the Darmstadt group in Germany, which are really well known by a thorough comprehension of the effect, producing materials, and so on. They are one of the top players in academia, the top player perhaps even in Europe. So Magnotherm fully dedicated to magnetic refrigeration. There is I think I took the slide, but I had it, but then I took it. There is a UK-based company called Camfridge. They have been going on for a while now, for what, about 20 years or so. They claimed last year that there was, so that they made a major release on, they showed basically a common refrigerator where they just substituted so it looked exactly like a normal refrigerator, where they just replaced the compressor and placed the magnetic field and the magnetocaloric material and all the heat exchange and so. And they claimed higher efficiencies in comparison with expansion compression. But well, so these are, let's say, emerging from the field. Then General Electrics, they at times they had a specific branch dedicated to these. They no longer have, as far as I know. And they were driving a lot of, let me even show you. Yeah, here it's a prototype developed by General Electrics in the US. Bayer, the Chinese, they are a huge player in refrigeration. From China, they also had a major project on these. So these, speaking of, let's say, outside but very large players of the industry. And then Samsung and some other Korean companies, they also had, as far as I know, they've been focusing of using these into air conditionings in cars. I think they have quite a lot of patents on that. Yeah, for sure I'm missing some more important players. For the hydrogen liquefaction, using these effects still. So the Helical, the European project, it's, I mean, going at good pace apparently. But the Japanese already have one, and the Americans also. So they already had at least a prototype which run for hydrogen liquefaction using magnetic refrigeration. Yeah, trying to see if I'm missing something. In terms of, but now a bit more academic terms, let's say, one of the interesting avenues to be explored is mixing these different solid state technologies. So applying a magnetic field, but then also pressure to maximize these delta T's, what they call a multicaloric device. That's something that people are pursuing. Yeah, so, but still the major challenges I would say are these, the fact that we need high magnetic fields, the cost of the whole thing, and now we will have to deal, I mean, this niche has to look around to other caloric technologies like the barocaloric that have been in the past 5, 6 years, been a lot of natures and sciences published on barocalorics. So they are getting really high values of delta T. So I think they will be a really good competitor of the magnetocaloric. Yeah. So
Thank
broadly,
you so much.
yeah, this is the view. For sure, I'm missing important players, but this is were the ones that came to my head. Yeah,
Thank you so much.
thank you.
Okay, thank you, Paniagua. Melvin, do you have any question, Melvin?
Oh, gracias, profesor. Por estos lados no tenemos preguntas, profesor. Solo saludos por la presentación.
Okay, Mel, thank you very much. And Luis?
Hello. Yeah, thank you very much, Joao. Very nice talk. Just your first slides, you show one video, and I didn't understood well the axis when you increase, apply the magnetic field, and then decrease and invert the magnetic. Yes, that one, the video. Yes,
It's constant.
it's time. The x-axis is time.
Time,
And
exactly.
the y-axis is, what is the
Temperature.
y-axis?
Sorry, temperature.
Yeah, the temperature.
Temperature
Okay, nice.
of the material.
On the material, exactly. Okay, and we see in the video, you show that it increases the positive and then decreases negative. So my question then is, what is the difference in temperature that increases and decreases? Thank you.
So this was I placed it here just as an example to show like a real life measurement of the effect. And so this is, to be honest, yeah, we can see here. We are at about 292 Kelvin starting temperature. When we apply the field and we move to 292.8. So roughly 1 Kelvin, 1.1 Kelvin increase. So this is an example of a measure of one of these points, Professor Luis. One of these points is the delta T measured adiabatically at, sorry, you are not seeing the laser. So one of these points is taken by one measurement similar to that one, where we look, so our material is at the base temperature, at this temperature, let's say. Then we apply the magnetic field. We see how much the material increased in temperature. Sorry. How much the material increased in temperature. And that is our measurement of delta T, so the temperature change of the material upon magnetic field application. And then the temperature of the material decreases, as you can see, like in an exponential kind of function, just because the material is warmer than the environment, so it's releasing that has extra heat to the environment. And the reverse happens for the last part. The last part, so the temperature relaxed of the material, we take the field out and we get a delta T, but now we get a cooling instead of a heating. And then, because the material is colder than the environment, it warms up because it's attracting heat from the environment.
It's always symmetrical, the one degree or 2 degrees.
Very interesting. Not really. Because of an interesting point. It's a bit harder to explain without doing. It's easier to explain with a graph. Let me try. Imagine, let's say that to pick this example here. Sorry. Can you see it's too small? Sorry. Yeah, imagine this point. So this is gadolinium under a 5 Tesla application. You started about, let's say this is 11 degrees, just to simplify, 11 Kelvin of delta T. So before applying the field, you were 11 degrees below. And those 11 degrees below, you were at 295, roughly. I mean, I'm just for the sake of example. 295, you apply 5 Tesla, you get 11 degrees. If now, immediately after, you remove the field, you would need, so you are now, sorry, before removing. So 295 plus 11 gets you to 306 Kelvin. right? Somewhere here. So if you remove the field, this is the delta T you will get. So it's not symmetric. It's not the same value because it cannot be. To be a thermodynamic reversible effect, this you have to always watch out at what temperature, initial temperature you are when you apply or remove the field. I'm not sure if I was very clear.
Okay, yeah, just okay. Yeah, I have another question because it's a long time for questions, huh? But it's a very quickly question. In one of the setups that you shown to explain, I don't remember for Sergio, that you show one strain gauge device.
Yes.
Yeah, you have the
Sorry.
setup.
It was a schema. It's just a schematic.
The schematic representation, yes, of the device.
Almost getting there. Sorry. Yeah. Yes, exactly. You are muted, Professor.
Sorry for basic question. For what you use the strain gauge device?
Okay. Yeah. The strain, so here in the scheme, the sample is represented in green, right? It's like a parallelepipedic, like a plate, let's say. The strain gauge is glued to the sample surface to measure how much of the sample, so the sample change in dimensions along a given direction. So this will tell us a bit, a lot on how the structural transition is occurring. So the material will expand or contract along the phase transition. And the strain gauge, it's our sensor of the structure. It has its limitations.
But you also show by XRD the dilatation, right? Different temperatures. It is changing. And with XRD, I think it's more accurate, right? Than
Yes. You are right. But to use these perfect, your point is very good. The XRD is a much better technique, right? To probe the lattice than the strain. Unfortunately, this has been done in high magnetic fields lab. There, the cryostats, it's you cannot access. There are no windows. I mean, there are some special ones where there are a couple of windows, but well, I'm gonna say it like this: it's virtually impossible to do simultaneously a measurement of magnetization and XRD in those setups. So, as we cannot do XRD, we decided to look at strain gauges. It's like the XRD would be better, but because technically we cannot install a source and a detector in that setup, we look at strain gauges.
Okay, thank you very much, João. Congratulations for the nice talk. Thank you, Isaías.
Thank you, Luis. Thank you, João. João, when Gisneider and Picharsky published that work, that first work in gasoline, blah, 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 they estimated the price of the magnetic refrigerator for domestic use at about, they need 1 kilogram of gadolinium, and it is too expensive. Nowadays, how is the price of one magnetic refrigerator, if possible?
I see. There, Isaías, Professor Isaías, the best paper is really that one, that reference that I showed here. It's by Rasmus Björk from Denmark. Sorry, getting there. It's not here. Sorry, it's below. Sorry about these. But I'll mention. So there in this paper by Rasmus Björk, they do a very careful techno-economic analysis of the refrigeration. It's this one. the lifetime cost of a magnetic refrigerator.
Yeah.
In this one, they get very interesting results such as this, that by far the largest component, the most expensive component is the magnetic field source. So the permanent magnet that is going to be responsible to apply and remove the field, much more than the magnetocaloric material. Here they considered, I think they also considered gadolinium, but they also considered the lanthanum iron silicon and the prospects. I mean, I'm no expert, so I'm just going to tell you what I read in the literature. The estimated price of lanthanum iron silicon, it's really low. Really low meaning less than $10 per kilogram. So in comparison with the magnet, that's really orders of magnitude of difference.
Okay.
Yeah.
Thank you, John.
Thank you.
If possible, everyone can open your cameras to thanks Professor João. João, we will have time to expand, think your last word for us today.
Oh, it's just thankfulness. So I'm very thankful for the invitation. It was really pleasure to present and to answer and comment and have this very nice conversation afterwards. So it's just thanking and I'll be sure to. Is it possible, actually, Professor Isaias? I can tell my students to come and attend these on the following Saturdays or
Yeah, I think so. But in order to enter in the link of this talk here, I need to ask Professor Luis Valadares because he is the Luis.
No, yeah, it's welcome. We need public, of course. Yes,
Okay,
welcome.
okay.
You can invite.
Because
Thank you.
another option is following in live in the YouTube.
YouTube.
Just transmitted online. But well, you and your studies are welcome to come in the next talk when you want.
Thank you. Thank you. So it's really just thanking you for this. Yeah, and with very nice time.
João, you can close your the slides for people appear better.
Sure, sorry.
So thank you very much again, João, and I hope go to Portugal and drink a wine with you in next moment. Okay.
Yes.
Thank you very much, João.
Thank you. Thank you very much to you all.
Bye. Thank you.
Thank
Hasta
you
luego a
very
todos.